Feel like a bit of a loser all around.
Well, John's prepped. He's got... so, John, right before you hopped on, we were talking about why can't I add fake facial hair and crazy hats via Google Effects to my face anymore. That's too bad.
Oh, you can't do that now?
Well, yeah, it's bugging out, and I can't do it now.
Oh, that's unfortunate.
But I can do this.
What? What's the point in all their big computers if they can't even do fake facial hair?
I know. All I ask is a cat in a hat. That's all I want.
Losers.
You taking notes by pen today, Matt?
I am. Oh, you can see that. Oh, yeah.
Transcribe them to the show notes.
I'd like to take minutes. We should really review the minutes from our last meeting, and then I'd like to. Somebody's going to need to move. What? How did that happen?
Wait, John's got a hat on.
I don't see it in my view, but
now it's off.
Oh, wait a second. Hold on. Let me try it again.
There we go. Huh,
yeah.
Why can't I have a hat?
Machine learning at its finest.
Here, let's try something like this. Hello, everyone. Welcome to Undersampled Radio, episode 26, the late night show, the late hour, with your hosts, Gorgeous Gobbler and Miracle Man. We're here doing the late night scene. Our guest today is John. I don't know. Okay, so it's later than we usually record for Matt and I. Our guest today is John Leeman. You may have heard him on our show before, or maybe on his show, Don't Panic Geocast. He's a star. He's a star, baby. Welcome to the show, John.
Hey, how's it going?
Good. I was attempting a new late night intro there because maybe I'll just have to edit that whole thing out. Because we usually...
I think that's a pretty fantastic intro.
You think so? I don't have a cool microphone to do it into. Well, like, if you can sound like you're the captain of an airplane if you cup your hand around the mic. I think it would just make my mic explode or break your eardrums. For those of you that can't see, John is the only one of us who is able to put on fake Google Effects hats and facial hair, and I'm super jealous. Matt, on the other hand, is now slowly sliding what looks to be a delicious beer into the frame and out of the frame. Matt, where are you?
I'm in Calgary, Alberta.
He's on location, reporting.
Yep.
What's live?
Yes. It's really nice here. I really like Calgary. This is the first time I've had kind of a lot of time to myself downtown since I lived here, basically, several years ago. And so I've been for a run by the river and seen some old friends and walking my old route to work kind of thing, because I used to live in this neighborhood.
Yeah.
And it's been kind of a trip down memory lane a little bit. It's been fun.
So did you get any work done, or are you just running around all over town?
Yeah, I've been also doing some work. I'm teaching a course this week, like a 2-day intro to Python with a bit of a data science kind of flavor. And I'm teaching the exact same course now again for the next 2 days.
Cool.
Yeah.
And they have you staying in a nice hotel room there? What is that?
Staying in, well, I stay in this very sweet little hotel right by the river in my old neighborhood. So it's kind of one of the, there's probably only 20 rooms in this place, I think. So it's quite nice and quiet. It's good.
Cool. Good. Well, we see John Scene is back there in his recording studio. He's got a much more professional setup than we do, and a cool hanging lamp in the background.
Which is to say that he's got a setup.
That's right.
I say it's really just a living room. Don't tell anybody, though.
It looks great, man. Matt is recording on a cell phone, so we'll see how the audio works out today. But our editor forgot to post the new podcast episode today, so I guess we're going to make him do that tomorrow. So it's been a crazy day. So let's get on to news here. There are literally zero bullet points for news, which is good because last show we had a listener write into the news section that there was no news going on. So we're just going to zip past that. What is GEB, Matt?
Oh, Gödel Escher Bach. You must know this book. I feel like everyone knows it except I've never read it before.
I don't know it.
By Douglas Hofstadter. Well, I was going to go and get it, but that would be deeply unprofessional after whispering Graham Gansel set up the show so professionally.
Yeah, you might knock over your cell phone.
Yeah, I'm trying to unplug these first. Yeah, it's hard to describe. I gather it came out originally in 1979, if I'm remembering right, and it won the Pulitzer Prize. It's kind of unlike many books, certainly, that I've read before. And essentially, I think it's called, the subtitle is sort of The Eternal Golden Braid. Mm-hmm. And Hofstadter takes this idea of the strange loop, which is essentially recursive systems, and sort of ties them into Bach's music and M.C. Escher's lithographs and drawings, which obviously, several of them have the idea somehow of a loop, like the famous waterfall that seems to go uphill, or the hands drawing each other, like that, sort of.
Right.
And tries to tie it into Gödel's, I'm probably mispronouncing his name, but Gödel's theorem about the sort of unprovability of arbitrary theorems given some system and set of axioms. And it's a little bit like idea or theorem of the fact that you can't compute when an arbitrary computer program will finish running, or whether it will finish, I should say. So these are sort of incompleteness theorems about which are it turns out, I think, incompleteness is an emergent property of these axiomatic systems. How's that?
It sounds fascinating. I actually have never heard of it, and I've now put a link to the book in the show notes so that you can download it there.
It's kind of a thick, it's a pretty heavy looking book, and that's what's put me off picking it up before a little bit, because I don't generally like big books. But it has got pictures, and that's the other prerequisite for me to read something, is copious pictures.
Well, Matt, this is inspiring me a little bit, because this is one of those books that I have carried around to 2 different apartments now since I bought it.
Right.
And have just not actually got to reading. It's been sitting on the nightstand for a while. So maybe it's time to pick it up again.
There you go. I'm in the same boat, or was, until my plane ride here.
Yeah, you could start a Software Underground book club.
Oh, that's a great idea.
Yeah.
Yeah. Let's do it.
Cool.
There's book 0.
I'm in. Okay. So
starting at 0, like a sane person. I like it.
Are we ever going to celebrate a milestone on this show? No. Okay, great.
Actually, prime numbers, we could do that.
Okay.
And we get lots of celebrations.
A couple. Milestone celebrations are going to get farther and farther apart as we...
So John, do you guys do milestone celebrations on of episode 50 or 500 or whatever you guys are up to?
Well, we did episode 42.
Nice.
Episode 42. Yes. So we did that, and we're actually coming up on episode 100. And we're not sure what we're going to do for that. We've had some discussion about it. I know the Mac Power Users podcast, they were commenting something about, they're well in the 200 or 300s now, and they said something about their episode 100 mugs. And like, we weren't planning to do mugs. Are you supposed to do mugs? I don't know.
Oh.
So we're trying to figure out what we're going to do for episode 100, whether we're going to go back and revisit some guests and catch up with them, or whether we're going to go back and play some of our favorite clips from the first 100 shows. It's a little mind-blowing to us that if somebody has listened to the show since the beginning, they've spent over 2 working weeks listening to Shannon and I talk.
Don't think about it like that.
I mean, it would be creepy in any other context, right?
Yeah, so just the working week time, or is that 24 hours a day?
That's just working week time, yeah.
Yeah, okay. They do get a break. You let them go.
Oh, yes, absolutely. But we've had a ton of fun doing it, and we don't plan on stopping anytime soon. But I think we may do something special for episode 100. That'll be kind of a big deal for us. Episode 99 is the 100th. But.
Okay, well, that's what I was going to ask. So it's index 99, but you'll be celebrating the 100th.
Right, exactly. Those
Nice.
off by one airs, they get you every time.
That's it. Oh,
Yeah, like the Mayans to the end of the world, right?
Yeah.
I just read that those are called Obi-Wan errors. Have you heard that?
No, I haven't.
Yeah. So that's what I call them now, Obi-Wan.
I like it. Yeah, Obi-Wan airs.
Hey, you guys
These are
want to hear
not the
about?
errors you're looking for?
You guys want to hear about my news or what?
Yeah, go on then.
Okay. All right. It's the next thing on the list. What are we gonna do?
Edit document.
Neural networks. I've been reading some more stuff about machine learning. There's links in the notes to Alex Graves' thesis, his doctoral dissertation that Matt posted on Software Underground the other day. It's awesome, and you can download it for free, or you can buy it for $149 from Springer.
Wow.
An extended version with one extra chapter. Yes. And the cool part is if you go
There's
to
an alternative ending.
Yeah. Just
Choose your own adventure.
Spoiler alert, the problem isn't solved. The cool thing, if you like spending money at Springer, like copious amounts of Springer. Well,
Okay.
never mind. But if you go to this website where there's a link in the show notes to the book, if you clear your cookies first, if you happen to visit the Springer website a lot, it learns what you're into. But if you clear those cookies first, you can get references to thing that I've been trying to do for a while, which is printed textbooks, which are modern and related to neural networks. So there's some good links on there if you do that.
What?
Yes.
Sorry, what was that bit about the cookies? How, who, when?
Oh, because,
Why?
if you go to Springer, they collect information about what stuff you're spending money on there. They collect information about what you're interested in, what you look at on the web page, and they make suggestions, recommendations based on your purchases.
Let's see.
Clear it, and then you can seed their algorithms with just the one book.
Oh,
You ever
I
do
see
that?
what you're saying. Yeah. No, that's cunning. So you basically, it's a way of
What's
getting
that?
recommendations. You're saying.
Tailored, yeah. It's not that cunning.
It's a tiny bit cunning.
Small.
It's good. It's small c.
Anyway,
It's cunning as a baby fox.
or whatever. Use your Tor browser or something. I don't know. Go check it out. John, you guys already know who John Leeman is, but I'll introduce him anyway. The last time that we introduced John on the show, it was in conjunction with Don't Panic Geocast, and we also had Shannon on the show, and we talked a lot about podcasting. And in the weeks that followed, I realized we didn't really talk very much about John's personal interests, which are all fascinating. So he is a doctoral student. He teaches, he researches, he reads, he writes, he podcasts, he builds hardware. It's amazing. You're doing all these different things. There's links on the show notes to his all various things, his Twitter and his LinkedIn, but his blog, particularly, that's been going on for years and years, which is everything is fascinating. His new company, Leeman Geophysical's site, and then he's on Software Underground too. I guess there's a lot to cover, but what is Leeman Geophysical doing?
Well, so we're trying to solve problems that generally involve instrumentation in the geosciences. We're always looking for these really small signals, things that are hard to measure, and scientists generally aren't instrumentation specialists and sometimes fall kind of prey to some of the problems that instrumentation can pose. You don't know exactly how this piece of instrumentation works, so you interpret some interesting blip that is really just an instrument artifact. And you would never know that. So I started Leeman Geophysical to address some of these problems, like looking for really small tilt signals, trying to extract some things from magnetics data. I haven't done too much with seismic, really, but I'm trying to build custom instrument solutions for people, or just provide general consulting services for lab or field deployments. So I've done some things with people controlling hydraulic rams and laboratory equipment, geochemical pressure cells, all kinds of things like that, where we're just trying to measure and do science correctly.
Instrument solutions. So I like the idea of sort of discussing the limitations of the instrument with the customer, right? So they get some understanding of what the feedback is going to be, what kind of limitations you have with respect to various inputs. How do you figure that type of stuff out?
A lot of it is just testing, because if you look at a data sheet for an instrument, or if you're building the instrument, you look at data sheets for components that you put into that instrument, like an analog to digital converter or a certain sensor. They have all of these headline specs at the top, and those are dreams, generally. Those are the ideal best case scenario in a Faraday cage in a testing lab that's far underground, or some crazy condition that we never ever get when we're doing science in the field or in the lab. So a lot of it is doing thorough testing. And you would be surprised how many little bits of firmware or little bits of data processing code that get included with instruments aren't formally tested. They're, okay, yeah, that looks about right. And it goes out the door. It gets shipped, which is a little scary. Or how many interactions are poorly described. Things like, okay, you're measuring tilt, but the temperature outside affects the scale factor for your sensor. It affects the null for the sensor. It can affect all kinds of different parameters that manufacturers either, well, they might do some kind of calibration for. If you're lucky, it's a 2 or 3 point calibration over some limited range. And they may not really capture the full response of the instrument, which is fine for a lot of applications. But when we're doing geophysics, most of the time, we really need to know the honest instrument response. So that's something that I do a lot of work with.
Is that something that these instrument manufacturers sort of anticipate, and they're trying to, I mean, I assume that it's a bit like software where they're trying to make something easy to use and, essentially thinking a little bit about the user experience, like plug and play kind of idea. But do any of them go out of their way to sort of say, well, here's the calibration, there's a special port or whatever, or you can fiddle about with parameters inside the instrument, or do they kind of leave that to the hacker to reverse engineer almost?
Yeah, that's generally how things come out. I mean, if you're buying, say an individual transducer, then of course you've got the calibration, you know how to talk to it. But if you're buying a completed instrument, no, it is to be treated as a black box in most cases,
right?
Which is unfortunate, because there are a lot of times where you say, well, if I could just change this one little way that this part of this instrument works, it'd be a lot easier for me to use in my application. A good example is I had a customer that needed to deploy an instrument for a year-long deployment on solar power at a very, very high latitude. So we would have long periods of low incoming solar radiation. So it needed to be a very low power instrument. They could buy an instrument that measured what they needed on the market, but no matter if you were reading it or not, if it was turned on, it's pulling 23 milliamps.
Right.
It's just sitting there running as fast as it can inside, taking these measurements and making them available. And then when you ping it with a serial command, it would dump data back to you. So if that were a situation where the manufacturer had opened up the firmware, or at least some hooks into it, you could go in there and say, okay, well, I want this instrument to power down, and I'm going to wake it up once every 15 minutes and take a reading and put it back to sleep. I would have been perfectly happy with that. Whereas instead, I actually ended up rolling my own custom instrument from complete scratch to take care of this.
So, and how might they if let's say someone was enlightened and they had this a way to hook into the firmware and fiddle with that, would that be through like a USB port these days or something like that, or or is it just very, very rare in the heart?
It's pretty rare. There are some instruments where, say, you could fire up some kind of program that they would provide you and hook up, probably with a serial cable still, and get your USB to serial converters out and maybe set some parameters. A lot of times it ends up being things like, well, you take these screws out and you take the cap off and you find this trace on the circuit board and you cut that with an X-Acto knife. And then you solder a wire from there over to here. they're pretty kind of kludgy hacks to get around stuff because, well, they didn't have to be versatile a lot of times in the past. We were looking for gross signals until the last few years, or we had all kinds of power. These things were plugged into walls, or we had generators, or we had big stations that we had set up with concrete piers and batteries and huge solar panels. Whereas now it's all about being able to rapidly deploy with a small footprint. And it's just something that we haven't adapted to yet. I mean, we're still using, RS-232 plus on a lot of these instruments, or custom protocols. You deal with some custom binary format from an instrument instead of a standard data format that's still common, as everybody knows.
And where's that, so are things going to, that seems like that creates a big opportunity for somebody who wants to sort of, quote unquote, disrupt the geophysical instrumentation market. Is that your plan, or do you see the future as more like Lego brick, custom built solutions with 3D printed enclosures and that kind of thing, so that actually there's no need to manufacture anything? You can just make what you need when you need it.
I think there's a place for both. There are certainly the custom solutions that are great to provide, and we can do that with 3D printing. We've got, CNC machining. I can design a part for a customer, show them the part in 3D online. We look at it, we say, okay, yes, this works. We assemble it virtually. I send it off, and the CNC machine part shows up at their door in about 10 days if it's not a rush job. So we can certainly do custom solutions like that, but there are some cases where you just need a bunch of instruments to go out and deploy. And so there is some manufacturing there. That's something that's been a challenge for me to get up on. I had a meteorology and geophysics background. I didn't have a double E or manufacturing engineering background. So learning, okay, how do I design the circuit board? How do I design it where it can be manufactured by pick and place robots in a factory? How do I design the enclosure for this instrument so that the CNC mill and lathe spend the smallest possible time machining it, because that all costs money? How do I work with, getting the parts designed, machined, shipped to someone else to be anodized, shipped to me for assembly? It's been a real adventure figuring kind of this whole design and supply chain process out.
Oh, that's really cool, though. And do you, is there opportunity there? When you sort of look out at the geophysical instrument landscape, what are you most excited about right now?
I think I'm most excited about getting real connected telemetering instruments instruments that can do things like mesh network together. So we don't go out and, in a traditional seismometer deployment, let's say, you go out, you either drag a bunch of cables if you're doing, say, an active source survey, right? These big takeouts. Or if you're doing, say, a passive survey, you dig this hole, bury these instruments, hook up to them with some crazy custom interface cable, program each one individually. You put in a compact flash card that's only a certain brand because for some reason no other brand works with this instrument. And you do that over and over and over again. And then as soon as you're done, you start making the loop again and collecting all these compact flash cards to get your data. Whereas we're starting to see solutions where, you get your gang of instruments together, you power them up, you pop open an app or some kind of configuration utility, you set up your network, it flashes to all the instruments, and then it's much easier to get data streaming back to you as well in real time from your network.
And that's reasonable, is it, from a power consumption point of view?
Depending on your application, yes. So, of course, transmitting does take a lot of power. It depends on how long you need to be out and what your power restrictions are. But for setup, for sure, being connected, wirelessly, being able to program all these instruments, definitely. As far as the mesh network passing all the data back, it depends. We have a professor at Penn State here that's been developing these things called geopebbles.
Okay.
And they
Pebbles are already geopebbles.
Hey, there you go.
Yeah. And they're a little bit bigger than pebbles. Let's see. I've actually got one here. Let me hold it up for you.
I think I want one of these things already. Yeah.
So you can see how big it is, roughly.
Okay. Yeah, that's bigger than that's a cobble. That's a small boulder.
Yeah, it's a little bit bigger. But this is a 3-component seismometer. It's got a little magnetometer and accelerometer in it as well. But they have done some active surveys with these where they would set a bunch out, they take their own orientation, they mesh network together, you hit the hammer, these record all the data, they can stream it back to you live, and you can watch the shot come in, all without dragging any kind of takeout cables or anything. So seeing things like that make me really excited for where we could go in terms of our level of sophistication.
It sounds exciting. It also sounds like this type of thing is being done in industry as well. I mean, am I wrong in saying that these sort of wireless node recording autonomous setups are much different than this GeoPebble?
I would say they're probably similar. They're maybe not quite as general purpose as the GeoPebble. This was designed from the get-go by their team to be able to be used for a very wide variety of applications, and it's all open source, so you can grab the firmware and hack it to do whatever you want.
Sweet.
Yes, I like that direction, and I also hope that we haven't really seen much in terms of opening up the source code for things, opening up the hardware design. I guess the other technology that I'd be really excited about is MEMS.
Mm-hmm.
So we're getting much better with these. So MEMS is micro electrical mechanical systems.
Mm-hmm.
And have you guys played with any of the MEMS sensors before?
Nope.
Well,
yeah, so these are like...
I've recorded data with them, or at least...
All right, yeah.
Yeah. I mean, it's really cool technology. One thing I'm curious about with MEMS, so maybe you can answer that in chatting about them, is the receivers that we were using were 3C MEMS, but they had an entire MEMS chip in each axis, whereas it seems like my phone can do from a single MEMS, and I gather that it does it from some signal to do with the torsional force on the single MEMS. That's how it can do X, Y, and Z. And I've always wondered why we can't do this 3D MEMS thing with a single MEMS in geophysical receivers. Over to you.
Well, that's a really good question. I'm not sure exactly what the answer is. If I had to guess, I would say it's a problem with the physical size of what they need to construct to be sensitive at the frequencies and amplitudes that we're interested in for geophysical applications, that you just cannot get the full 3C on a chip and get that kind of frequency response. In your phone, like you said, they're all 3-on-1, and you can buy these chips for $3 to $5 in quantities of 10 or less. They're incredibly cheap. What I'm really excited about, though, is there was a paper in Nature this year about a gravimeter that is MEMS-based that they've built. And this gravimeter is able to detect earth tide with a MEMS chip.
Wow.
So they're saying, this is probably going to be $1,000 to $2,000 when it hits the market, which I hope is soon. But knowing the speed of silicon development, it will probably be waiting for a little while still. But you think about this, sure, it's not as good as a CG5, but it also costs $1,000 for the chip.
Yep.
So now, okay, but
so that
I
would
thought
be
that one of the things about MEMS is that they kind of are capable of measuring down to DC, which is basically a gravy meter. Sorry. But so how is an ordinary MEMS not a gravimeter?
Well, just not sensitive enough, right? So this is a setup where they have a test mass sort of engraved in this silicon, and then they have a cantilever spring on top, and then some anti-cantilevers on the bottom. So it's like a spring that has a non-constant K. As displacement on the mass increases, K actually goes down. And so they can get this to be incredibly sensitive. And what they end up doing, which is a beautifully simple solution, is this test mass is moving, and they need to be able to tell how much it's moving. So how do you do that in a MEMS device? Well, you could use the capacitive technique where you've got the two structures, but that's not going to give them resolution they need for a reasonable size. So they just put an LED on one side and a receiver on the other, and the test mass acts as a gate, changes the amount of light from the LED that's allowed to fall on the receiver. And lo and behold, that's great as long as this thing is all ovenized. It's got a little PID control loop that keeps it stable to about 1 millikelvin, and they get a beautiful signal. It's just absolutely incredible. And you think about this, we could we could put this on all kinds of autonomous sensing platforms, right? So you put this on your autonomous submersible, you put this on your drone, you put this on any kind of thing. If you're going to fly a survey or do any kind of survey somewhere, and these are $1,000, $2,000, just take the data.
Yeah, because it basically has no response time and it's real time.
Right.
Yeah, that's crazy.
Yeah, I think there will be some vibration problems when you're trying to put these on, like a drone.
Yeah,
that's going to be the isolation on that will be tricky. I'm not sure how they're going to get around that just now, but that's one thing that's going to be really exciting is we see that, and the price of these comes down, right? MEMS sensors, MEMS accelerometers used to be pretty expensive. Then the smartphone market made them very cheap. You can have magnetometers in your phone that work as pretty decent metal detectors. And the price of those is coming down, and they're getting higher and higher resolution. Accelerometers are following. So here pretty soon, we're going to be able to have an entire MEMS geophysical sensor suite for not a lot of money.
Right, and I think the magnetometers used and the accelerometers are used for sort of rotation and that kind of sensing, right? In a cell phone context. So it seems like you need to come up with a really good reason to have a gravimeter in a cell phone.
Right. Yeah.
Right? I mean, like if there's a reason for games or porn or something, probably that'll have that. You can have a $5 gravimeter chip.
Oh yes, you just have to get one of the big industries behind it, right?
Yeah.
So a thought occurs. There's a pain point for customers not being able to accurately predict the sensitivity of their instruments over a variety of field conditions. Is it a feature or a bug of the suppliers to have this, in their workflow? Like, would it be beneficial for some company, Leeman Geophysical, to record data, real field data about various instruments and provide that data as a service back to the manufacturers?
Oh, absolutely. I think saying, okay, we're going to go out in these controlled conditions and we're going to put a suite of instruments out, some of which we know the response function of very, very well, and your instrument X, that we think we know the response function of reasonably well. And we're going to come up with a real response function for you. We're going to come up with a good calibration for you. And we're going to test several of your instruments and tell you, is your manufacturing process putting out instruments that are self-consistent, that have low drift, that have low offsets from each other? Or are you going to have to calibrate each and every one of these individually and stamp them as they go out the door? Because that's a significant extra cost for you.
Mm-hmm.
Yeah, right.
Another one is looking at some products that are already made and think, how can we make this better or easier for the geologist or geophysicist? There's an example. Shannon does paleomagnetism, where she goes out, and we talked about her rock drill when we were all together. It's the episode Rock Drills and Beer, right? You go out and you would use this drill. It would cut around a core of rock, and then they stick this orienter in the area where the drill just was to measure the orientation of the core. So you would stick this device in, you level this Brunton compass, you take the reading off the Brunton compass, you take the rake angle, and that little piece of metal that goes in the hole and you can tilt the Brunton compass on to level it is $700, not including the compass. And it's a piece of metal with some laser engravings on it. Well, I said, okay, well, how accurate do you think you can read that?
Yep.
Oh, maybe a degree. We'll believe a degree. Okay, well, I can take a MEMS magnetometer, have you do one of those simple calibrations like when your phone has you wave it around in the air, and I can get you within a degree, and all you have to do is stick this thing in the hole, press the button, it goes beep, it's written to an SD card, and you move on to the next one. Right. So solutions like that are something that I really want to implement, make field work faster, more reliable, a little bit less of the, did you say that was 273 degrees or 237, and then you still write it down wrong, and you get back to the lab and nothing makes sense? And try to eliminate some of that. So try to come up with unique physical user interfaces to instruments.
Yeah, really cool. It's so interesting, and it's something that I feel like the office geoscientist, we really take the data for granted. Essentially, we treat it as
Truth.
Well, truth is a bit of a stretch, right? Because you know that it's not true, but you think that at least it's consistent, say, from one set of readings to the next, and that it's basically self-consistent. I think how you just put it earlier. You know, that it's as far as it goes, it's reliable. and it's really easy to forget. Like anytime you sit with a petrophysicist and look at logs, for example, they're like, yeah, but that was recorded with the GRX-23, and oh, look at the date, it's 1984. They're probably using such and such a kind of mud, and you're like, okay, I don't believe any of my data at all anymore. And
exactly.
Yeah, but they know that stuff, right? It's a lot of it's encoded in human. Like I feel like we've not done a great job of bringing that, what would you call it? Almost like contingency metadata along with the data. And I sort of feel like, well, if the instrument maker knows this, why don't they just correct it? Or, there's this sort of feeling that, no, the customer should have the raw data, and then it's up to your petrophysicist or whatever to implement models or do whatever they want to correct stuff. And I just feel like it's a really tricky area, and you almost need a guy like you sitting next to you going, yeah, but what was the temperature on that day? It's like, I didn't realize I had to worry about the temperature.
No, it's a great point. And I think the reason people don't do it is because it's hard, and it's a lot easier to, plug your ears and pretend like it didn't matter. There are several data sets that I've seen where people say, oh, look, I've recorded, one of them was an initial, somebody said, oh, I've figured out a way to make a cheap gravimeter that can measure earth tide. This was before the MEMS sensor. And I'm not so sure about that. Looked at the data, and it turns out once you actually run a model, which is also something that people seem to not necessarily do, and they say, oh, I've got this fantastic, okay, well, did you run a model and compare your instrument to the model? You do that, and it turned out to be exactly that, Matt. They did a very good job of measuring their HVAC system, because their instrument was a very, very nice hygrometer that was sensitive to when the HVAC would come on and dehumidify the air.
Right.
Yeah. Well, so there's all kinds of weird
silver lining.
Yeah.
Well, let's talk about modeling a little bit. I note that you do a lot of modeling, and this has to do with Leeman geophysical stuff and also with modeling of faults and fractures and things like this. So I guess this is a two-part question, and we'll start from the instrumentation side. You do modeling of pre-build modeling using CAD and I presume SolidWorks and things like that. And you also do actual numerical modeling for instrumentation response. So give us a little rundown of what you do in those instances and why it's important.
All right, so let's start off with the CAD part. You said SolidWorks, which is what I initially used for a lot of my CAD, but you have to remember that I can't really use the university licenses that I'm a student at for anything that I'm doing for my company. So I couldn't afford SolidWorks because that is very expensive for a small person like me that's starting up and trying to get this company going on a graduate student budget. There's a company called Onshape that you should check out if you're interested in this. They are some SolidWorks engineers that broke off from SolidWorks, started this company. They're up in Dedham, Mass. And it is SolidWorks in the browser, in the cloud.
Ooh.
Yeah, and if you want to use it as a hobbyist, it's free. And if you want to use it as a professional, I think it's $100, $120 a month, something like that. It's not horrible. And I have not really encountered many things that I said, oh, I wish I had SolidWorks for this. And they're very responsive. When I was working on an instrument design, I needed to do some O-ring grooves. And I said, SolidWorks had an O-ring groove tool. And that was really cool. Here I had to draw the profile of the groove and make it on a plane and rotate that around. And it took me a little longer. And sent that in as some feedback. And lo and behold, a couple weeks later, they said, oh, hey, there's an O-ring groove tool now. Enjoy. And it's really cool that they are working with their customers. They iterate so fast. And since it's all on the cloud, I always have the most up-to-date version of the software. And the numerical modeling part of it, say they have a partner company that does the finite element simulations on these parts. So I'm not tying up my computer. I can sit somewhere with a decent internet connection on a MacBook Air and hook my 3D mouse up and start a numerical simulation of some part, and it's all running on their infrastructure. Then I close my laptop and go get some lunch and come back, and the simulation's done. I can look at the results.
Okay, John, what just help me out there. What do you mean? What's a numerical simulation on a part?
So you can do things like load it. You can say, I'm going to apply a point load here. I'm going to put an internal pressure in this pressure cell.
Physical stress.
Yeah.
Yeah.
So I'm simulating, if this part, let's say it's for some kind of a material testing machine where they're going to try to squeeze something and see what happens. I can model that entire system and say, okay, we're going to get so much deflection here and here. There's a stress concentration here that could be a problem. You could have a fatigue issue there in the future. Or, well, this bracket's going to break. We need to rethink the design of that because it gets overstressed under these conditions, that kind of thing.
The first time I messed around with SolidWorks, I played with it for, it must have been 8 hours, because you do all these crazy things like, so SolidWorks is a PDE solver, and it's got, like thermal loading and diffusion of thermal energy. So you can build an electronic circuit in there and see how hot pieces are going to get based on what they're built out of. It's just cool, and see it all visually. It's very cool.
Oh, and they've got some CFD stuff, so you can say, I'm going to put that circuit board in an enclosure with some vents. Show me how the air is going to move inside the enclosure. Now I'm going to put a fan in. Show me how the air is going to move. What parts aren't going to get adequate airflow? It's amazing.
So I'm at the Onshape website here, and can you do that type of stuff, the PDE stuff, finite analysis?
You can. They have like a plugin. It's almost like their own app store sort of thing. Mm-hmm. And there's another company that they work with very closely that you just activate the plugin, and they give you some ridiculous amount of free computing time to get started with it. And then the computing time is relatively cheap after that. I would recommend, and they've got some really nice tutorial videos. So if you don't know anything about 3D modeling, go watch their tutorial videos. It'll take you half an hour, and you'll be able to design basic parts.
So
pretty quickly.
As you may know, I'm building a dune buggy at the moment.
Right.
One of the coolest things that I did in the planning phase is I built a 3D model of the roll cage that I'm going to put on this thing, and I stuck it in VR. And so I put a chair that's the right height in the middle of my office, and I sat down inside of the roll cage model.
Oh wow!
And I could see. Oh, actually, that bar is too close. It's going to hit me in the head, or whatever. And so I would change the model based on the actual physical dimension of the thing. So it would be very cool to be able to combine the PDE solutions and the VR realism. Yeah.
Yeah. So I'm curious, what kind of headset do you use for this?
I have a Vive, HTC Vive.
Okay. Yeah. I keep toying with the idea of getting a VR headset and just haven't yet. I keep thinking, I'll wait just a little bit longer and see what else comes out. And I've said that for a while now.
It's worth it.
Yeah. I need to just break down and pick one up.
It's a lovely thing. I've had so much fun learning about not specifically modeling, but mesh rendering and volumetric texturization and things like this. It's been a fascinating process. I built a little, they were asking about on seismic, on the Software Underground the other day. I built a seismic VR visualizer, which was kind of a fascinating project. So I'm using it for, various things, show off data to clients and do stuff like that. So I can deduct it, justify it that way.
So you put in the notes that you had something about LiDAR scanning. So is that something that you mess with?
Did I?
Yeah.
Let me just get back to that.
You said it was your dream to combine LiDAR scanning and 3D modeling.
Okay. So I have one of several dreams is to do some sort of automated, and it's already being done, but to do some sort of automated modeling that represents data visually or tangibly in VR space. And so this is already being done in many applications, one of which, the most recent one I played with the other day, was the Google Earth suite is now gone VR. So, their 3D modeling of cities, of buildings, of trees, of things is automatic. But it's not, it has low resolution.
Right.
It's not LiDAR, right? So wouldn't it be cool if you could do, and this is not an original idea, obviously, you could take a human being, walk them into a room, or better still, walk around a human being in a room and automatically populate your VR space with a physical scale accurate model. And if you combine some visual detectors with that, some cameras, a 3D camera, texturize it automatically as well.
Yeah, I think that'd be a lot of fun. And LiDAR is something that I haven't had a huge chance to play with a lot, but there's this Kickstarter project that I backed a while back. It's called Sweep. It's supposed to ship, I think, the end of the year or so, which probably means sometime early next year. Everything gets delayed, right? But it is a cheap, or inexpensive, I should say. It actually looks like they're doing a pretty good job building it. Little scanning LiDAR that just takes these, 2D slices pretty rapidly. And so I ordered one. I'm going to do something fun, like put it on a drone and see what I can do with it. Just see what happens. It looks like it'd be fun, and for a couple $100, it was worth a shot.
So, related to these two things, I'm struggling to remember the name of it, and I don't have a computer in front of me. But I think it was called Cartographer, something like that. It's Google software project, and it's the thing they're using to 3D image the interiors of buildings and museums and shops and that kind of thing. And it basically automatically builds up a 3D model of an interior based on LiDAR.
Mm-hmm. Wow. They walk it through, they push it through on a cart, right?
Something like that, yeah. Or a backpack, I gather, in some places. And I think it was called Google Cartographer or something like that. And they just open sourced that like maybe 3 months ago.
Oh, I didn't know it was open source. You can see it.
I didn't either.
Tell me if this is on the open source page, if you know. But there was a video of them doing this, maybe in the Louvre or something. It was
right,
a year or two ago. But that's exactly what I'm talking about, and so I'm looking at the Sweep Kickstarter too. It just
it looks cool, and maybe there's a lot of neat stuff going on with structure from motion right now too. Where you take all the photos and put them together, try to make a 3D point cloud based on that. There's a project called Open Drone Map that you can download, compile, and feed it a bunch of photos, and it will spit out a point cloud.
Oh, cool.
Okay.
Pretty decent job. I'm planning on writing up a little bit on that. To put a camera underneath a quad and just have it take some photos and see how good we can do at rebuilding that point cloud. So maybe a virtual outcrop. It's something we talked about in the channel a while back.
There's a chap. I'll try and connect you with this chap. I think he's not in Software Underground, but he's definitely on Twitter. He was at University of New Brunswick, but I feel like he's at some kind of startup now in New Brunswick, doing exactly what you're talking about, and it's virtual outcrop, and they're imaging mines and that kind of thing. With this kind of technology, but he's very forthcoming about what their methods and stuff, and it's very chatty on Twitter. So I'll try and remember to connect you guys.
Yeah, that'd be great. I mean, and there's a lot of applications for an airborne scanning LiDAR, or even structure from motion, where you look at some of the industries like the power industry, right? These coal plants have huge piles of coal outside them. And most of them right now pay an aircraft, with a person flying it and one person sitting in the passenger seat, to fly over every couple months, photograph, and then they have somebody sit down and estimate from these photographs the volume of coal that they have on hand. You could program a drone to have a flight path to do this, put a LiDAR, take some structure from motion data, and just do it automatically at a fraction of the cost and less hazard.
Yeah, and way more often. Like you could have much more sort of granular.
Hello.
You see that one coming. So I should have asked this earlier, but I don't want to miss the opportunity to ask you about. Do you know much about distributed acoustic sensing And is it all it's cracked up to be? Because people are really, really banging on about it in exploration geophysics.
Yeah, so DAS is pretty cool. This is the idea that you've got a fiber optic cable, and you have what's called an optical backscatter reflectometer, an OBR, that sweeps a laser through a range of wavelengths, measures the backscatter coming back out of the cable, and from that, at many points along the cable, gives you what they call a TSV, which is temperature strain value. In the early iterations of this system, which is what I had a chance to work with, there were actually these Bragg gratings embedded every 1 centimeter in the cable, and reflected was slightly different for each. So we would sweep the laser through, you would get a peak from each grating, and you do that over and over again and watch the peak shift as the cable was either strained, compression or tension, or as the temperature affected it. When I was doing that, I was actually interested in the temperature, so I tried to ignore all the strain and cancel it out because I was using this as a distributed temperature measurement system inside a giant 72-liter pressure vessel.
Right.
At that point, the sampling was not near as fast as it was now. We tried doing some crazy things like whacking it with a hammer and seeing what we could get out, but it just didn't have the response that they do now. I've seen some data from the DAS systems where they would put the cable, say down a wellbore, and then have basically a rubber sock that they would pour water in or some heavier fluid in, inflate the sock that would hold the cable against the wall of the well. This is all shallow stuff to couple it, and the data looked gorgeous. At AGU, they had somebody demoing one of these systems a year or two ago. Got to go up and play with it a little. I was really, really impressed. The cables used to be very fragile and very expensive. It seems like they've got that problem at least somewhat solved now, where they're only somewhat fragile and marginally expensive.
Well, yeah, and I gather that they're totally ordinary fiber optics. It's a single fiber. And
right.
It turns out that many wells are instrumented like, oil sands where there's a thermal recovery method, right? So temperature is actually a really salient thing. And now there's, probably, I don't know, thousands of wells instrumented with fiber optic, and they're sort of finding, hey, we can actually do acoustic measurements and acoustic imaging from this sort of data. It's totally sounds just so far-fetched, but seems to work.
Yeah, I mean, these are all things the optical engineers tried to get rid of, right? They didn't want their cable to have anything reflecting back, and they wanted this perfect cable, but their noise turned out to be our data.
Yeah, right. There's like a seismologist standing next to the engineer going, hey, can I have that stuff you're not interested in?
Yeah, exactly.
How you said the lasers were sweeping through frequencies. I thought lasers were like mono frequency, and that was kind of the whole thing about a laser. So how does that work?
I'm not sure the physics of how they actually do this. I think it's different for the different units. And the one that I worked on was manufactured, like 2001 or something. It was one of the very first systems. So I'm sure they do the sweeping in a little bit more efficient way now. That's how they're getting the higher sample rate. We had a unit that was, I would say, a 4U rack mount unit. And it took us something like 30 seconds to sweep 8 cables. So it was not an incredibly fast unit. I know that same company has done some things now where they have multi-fibers, and they're able to do shape sensing of the fiber. So you could wrap the fiber. They had a demo that was very cool. They had a 2-liter bottle of Pepsi. They wrapped the fiber optic cable around it. On the screen, you could see them wrapping the cable around the bottle. And then they shook the bottle, and you could watch an exaggerated expansion, the strain on the bottle from the pressure buildup inside.
Oh my goodness.
That was kind of that was where the technology was at when I left actively using the fiber system. I haven't had a chance to use it professionally since then, unfortunately. But it seemed incredible. We had one of the first systems when we were playing with it, and we were using it in these huge pressure vessels under 2,500 PSI of methane pressure. So a very hazardous environment. And we had great luck with it. It was amazing.
I imagine you don't want electronic instruments particularly, right? So having like actual
having high-powered
lasers
is awesome.
Yeah, no, it was amazing. You know, all that could be out of the room. We had to have anything that was active outside of the cold room where this pressure vessel was. We were simulating seafloor conditions. So we were at 2 Celsius and high pressure. We were making methane hydrate in an artificial sand column.
Right.
Cool. And then simulating its destabilization. Well, one of the early things we did before they had the shape sensing fibers was tie this fiber to pretty much a country cross-stitch grid. I think we went and bought it at a craft store, but we wrote it up as something clever like rectilinear plastic, something. But it was really just a plastic grid that we tied this fiber to, did a little bit of math so we knew where each sensor was on this. And one of the first tests was I just put my hand on it, and you could see very quickly the shape of my hand come up on the screen in this interpolated image. And we were just stunned by it as an incredible technology.
I love that. It's so sort of unintuitive, and it really makes you think, oh, wow, maybe it's not. I mean, geophones have been around for so long, right? And thermometers, right? and actually, there are many applications where those things are not reasonable, or they're not high. You can't put enough of them out there spatially, or for sampling. And I love how people are just totally, when people completely rethink the way that sensing can happen,
we're talking.
I just figured out what Matt and I are going to do for our 100th episode.
What's that?
We are going to have a 2,500 psi methane tank destabilize in spectacular fashion. Would that be a good firework?
That sounds like quite a party. Yeah.
Matt's got one more question for you here at the end. Go ahead, Matt.
Oh, right.
You don't have your paper in front of you.
I don't know, but I wish we'd been asking this question kind of all along. So I think we should make a thing out of it. I wanted to ask. So one of my favorite sort of topics.
And we're losing Matt. Oh, sorry, say it again, Matt. We lost. You cut out there for a second.
Okay, so it's about unsolved problems, and I wanted to ask John, what are the greatest unsolved problem or problems that he perceives in geophysics today?
Oh boy, that's. I guess you could come up with one for almost any subfield, right? So my research has focused on earthquakes and earthquake interaction and fault stability. So I'm going to go there, just because that's, I would say, the field that I'm most familiar with. I think one of the greatest unsolved problems we have right now is fundamentally when you're sitting on a fault, when you're looking at the mechanics going on on the fault, on the frictional surface, what is the universal equation or properties that describe how that fault is going to behave? So how do fault mechanics really work? We have all of these relations. I use the rate and state friction relation in my work all the time, which is an empirical equation that we fit some parameters to that we call A and B because we're creative. And we say that describes how friction works on a fault, and that combined with some kind of stiffness that nobody will tell you what it is. Is it the stiffness of the rock? Is it the stiffness of the gouge? Is it what's the stiffness? We say, you put those together and you can sort of describe maybe whether when the fault fails, which we still have no idea when that's going to be, how it's going to behave. Will it have a slow earthquake? Will it have a fast earthquake? So coming to the governing equations for the physics of how earthquakes happen. We have the high-speed physics sort of down. We have the low-speed physics sort of down. We have no universal equation. And if you tell me that physics fundamentally changes based on what speed a fault is moving at, then that just means you have the wrong set of physics. So I'm going to say fault stability. That's my unsolved problem in geophysics, and it's got a lot of impacts.
It's a time and space problem, it sounds like.
Yes, definitely. So there's just the large earthquake in New Zealand. It was about a week ago now, and that shows that we have a lot of things we don't understand. It was a pretty complicated rupture, It started in one place, it propagated for a little ways, then it actually hit the subduction zone. There was some major thrust movement on the subduction zone. There were some really weird phenomena associated with that earthquake that we don't understand at all, like earthquake lights. I don't know if you all saw the video.
Oh, no.
There were earthquake lights associated with this earthquake, which 40, 50 years ago, the geophysics community thought that they were a made-up thing. And then there was some photographs from an earthquake sequence in Japan. I said, oh no, these are real. And now in the day where everybody's... it's an electrical discharge during a large earthquake. It's very similar to lightning. And maybe, I would say in the 70s, they became accepted as being a real phenomena, but nobody really knew why they happened. There's those things we still really don't know why it happens, but there's all kinds of strange lines of evidence pointing towards it and showing that there are all these processes going on faults that we barely have a clue they exist, much less understand what is actually causing them.
So would your grand unified theory of earthquakes and fault ruptures, would it include even a sort of electromagnetic phenomenon, or is that too far?
I think it would have to if you had a complete theory, right? I mean, you're looking at a way to release energy.
Yeah. Okay. Yeah. Right.
Yeah.
Right. It's part of a frictional sort of event, right? I get maybe.
Yeah.
Is lightning to do with is it a frictional effect essentially? I don't really know much about lightning. Like what generates that
lightning,
charge?
You get things colliding and charges separate based on the size of water droplets or hailstones and that kind of thing in the atmosphere. That generates a charge differential. In the Earth,
like a balloon on a jumper, right?
Right.
It's the old rub the balloon on the jumper trick.
Right.
It's exactly the same thing.
Well, so in the Earth, there are several theories. People have said piezoelectricity, which everybody sort of agrees with now. That won't work. The theory that's out there right now, and I did a little bit of work on this on the very first part of my PhD, which was a fun intro project, sort of, is this semiconductor type theory, where as you stress a rock, you get electron holes migrating in the crystal structure and end up separating these charges. And that theory isn't very widely accepted. I mean, I didn't come up with it. I tested many theories that were out there in the literature, and that's the only one that I couldn't disprove. But I certainly couldn't prove it either. And I agree that it may not be the right theory, but nobody's come up with anything better yet. But it's one of those things that probably tells us something about the stress state on the fault. And it is a mechanism to release energy, though a pretty small amount. You think about it, 10% of the energy released in an earthquake is seismic energy. So not a whole lot is what we actually get.
Wow. Unsolved Problems in Geophysics from John Leeman. That is a good one. That's a nice closing thing here. I think that's a good idea, Matt. John, thanks for coming on the show. I feel like we could talk for another 3 or 4 or 5 episodes. but
thanks for having me.
Yes, thanks for coming. Matt, do you have anything else to wrap it up?
I do not. Thank you, John. I really enjoyed that conversation. It's fascinating. I still I've only crossed out about half of the things on my piece of paper. So see you next time.
Everybody that's listening,
absolutely.
Tune in next week. We're going to have an open source Undersampled Radio. We're just inviting anybody who wants to come on board to come talk to us. Go to the Software Underground or the Undersampled Radio Twitter feed to find the document where you can come join us. Until then,
very cool.
See ya.
Peace out. See ya.
See ya.